Tiny galaxies hold immense secrets that could rewrite cosmic history. These dwarf galaxies are the universe's unsung heroes, small in stature but colossal in their mysteries. We are about to journey through 25 of their most bizarre and mind-bending discoveries. By the end, you will see the cosmos in a completely new light. Why do some of these galaxies appear to be made of almost nothing but invisible dark matter? How can others survive with no dark matter at all? What forgotten truths about our own galaxy's birth are they hiding? The answers challenge everything we think we know. Are you ready to question the fabric of reality? Our journey begins with a fact so strange it defies intuition. The smallest galaxies in the cosmos are not dominated by the stars we see, but by something we cannot see at all. These dwarf galaxies are composed of up to 99% dark matter. That makes them the most dark matter-dominated objects ever discovered. Imagine a city where for every one visible person, there are 99 invisible ghosts holding everything together. That is the bizarre reality of a dwarf galaxy. The stars we observe are just the glittering tip of a vast, unseen iceberg. How did astronomers even uncover this ghostly majority? The answer lies in the motion of stars. By measuring how quickly stars orbit within these small galaxies, scientists found something shocking. The stars were moving far too fast. According to the laws of gravity, the combined pull of all the visible stars and gas should not be strong enough to hold onto these speedy stars. They should have flown off into intergalactic space long ago. The only explanation is that an immense amount of invisible matter is packed into the galaxy, its gravity creating a powerful glue that holds the entire structure together. This discovery transforms these tiny galaxies into perfect natural laboratories. They are the purest places in the universe to study the properties of dark matter itself. With so much dark matter and so few stars to complicate the picture, we can finally test our theories about what this mysterious substance actually is. Does it interact with itself? How is it distributed? The answers are hidden in the silent dance of stars within these cosmic ghosts. But this ghostly dominance of dark matter leads directly to another, even deeper cosmic puzzle. For decades, our most powerful computer simulations of the universe's evolution have told a very specific story. When you model the growth of a giant galaxy like our Milky Way, the physics dictates that it should be surrounded by a vast swarm of thousands of dwarf galaxies. These tiny satellites should be buzzing around our galactic home like bees around a hive. Yet when astronomers look up, they only find a few dozen. The overwhelming majority are simply missing. This glaring mismatch between theory and observation is known as the missing satellites problem, and it strikes at the very heart of our understanding of cosmic structure. So where did all those galaxies go? One compelling theory suggests our assumptions about dark matter itself could be wrong. The standard model uses what is called cold dark matter, particles that move sluggishly and clump together easily. But if dark matter is actually warm, meaning its particles are faster and more energetic, it would not clump as readily into such vast numbers of small halos. A warmer dark matter would naturally produce far fewer dwarf galaxies, potentially aligning our simulations with the empty skies we actually see. Another possibility is just as fascinating. Perhaps the dark matter halos are all there, exactly as the simulations predict. But what if most of them failed to light up with stars? In the violent early universe, a background of intense radiation may have blasted away the precious gas from these small, fragile structures. Without gas, there could be no star formation, leaving behind a population of completely dark, invisible galaxies. We would have a universe filled with ghost halos, perfect dark matter spheres that contain not a single shining star. This means the cosmos could be far more crowded than it appears, a hidden metropolis of dark matter cities we are only just learning to detect. The ghostly dominance of dark matter creates galaxies so faint they almost are not there at all. We now enter the realm of the ultra-diffuse galaxies, cosmic phantoms that defy every expectation of what a galaxy should look like. Picture a galaxy the size of our own majestic Milky Way, a sprawling disk of stars spanning 100,000 light-years. Now remove 99% of its stars. What remains is an ultra-diffuse galaxy, a vast, wispy cloud of starlight so ethereal you could look right through it. These are not small, dense dwarfs. They are galactic giants that forgot to put on any weight, colossal yet ghostly structures that hold one of the universe's most perplexing secrets. One of the most famous of these phantoms is a galaxy known as Dragonfly 44. Located in the distant Coma cluster, it is a titan in size, rivaling the Milky Way. Yet it contains only 1% of our galaxy's stars, a mere sprinkling of suns scattered across an immense void. This staggering emptiness leads to an even more incredible fact. Calculations show that Dragonfly 44 is 99.99% dark matter. For every single atom of visible matter you could ever hope to see, there are 10,000 particles of this invisible substance holding the entire ghostly structure together. It is a dark matter galaxy with a few stars tossed in for decoration, a cosmic paradox that should not exist. How can something so large, so fluffy, and so empty possibly survive? Galaxy clusters are violent environments, full of strong gravitational tides and searing intergalactic gas that should shred a delicate object like this to pieces. The fact that we see ultra-diffuse galaxies like Dragonfly 44 at all means they must be anchored by an incredibly dense, tightly packed core of dark matter. It is this unseen skeleton that provides the strength to withstand the chaos of the cosmos. Their formation is a profound mystery. Did they form this way as puffy failures in the process of star creation? Or were they once normal galaxies that had almost all their gas and stars stripped away by a violent encounter, leaving behind only their dark matter heart and a fading memory of stars? Each of these nearly invisible ghosts is a silent challenge, a question written in faint starlight that we are only just beginning to read. But if some galaxies are mostly dark matter, could others be made of nothing else at all? This brings us to the ultimate cosmic ghost, the dark galaxy. Imagine a vast island of dark matter, a gravitational well so deep it could hold an entire galaxy of stars, yet it remains completely and utterly black. Not a single sun shines within it. This is the theoretical object astronomers call a naked dark matter halo, a structure that somehow failed the fundamental act of galactic birth. For decades, these were merely a hypothetical solution to the missing satellites problem, but the evidence for their existence is growing stronger. We detect them not by the light they emit, but by the light they bend. When a background quasar's light flickers in an unexplained way, or a distant galaxy's image appears warped by an unseen mass, the culprit could be one of these invisible halos. Their gravity acts as a lens, distorting the fabric of space itself and twisting the light from objects far behind them. We see the effect, but we see no cause. Other hints come from lonely clouds of hydrogen gas drifting through intergalactic space. These clouds are rotating at tremendous speeds, moving as if they are part of a much larger, massive object. The gas alone does not have enough gravity to hold itself together at those velocities. It must be embedded within a massive, invisible structure, a dark matter halo that provides the gravitational anchor. Finding a confirmed dark galaxy would change astronomy forever. It would be the ultimate validation of our dark matter models, proving that the universe builds far more skeletal frameworks than it ever fills with stars. It would give us a perfectly pure sample of dark matter, uncontaminated by the messy physics of stars and gas, allowing us to study its distribution and properties in isolation. We would finally have direct proof that the cosmos is filled with these invisible cities, a hidden architecture underpinning everything we see. These cosmic ghosts hold a chemical secret, a time capsule written in the elements of their stars. When astronomers analyze the light from dwarf galaxies, they find a profound and ancient simplicity. The stars within them are overwhelmingly composed of just hydrogen and helium, the two primordial elements forged in the Big Bang. They possess strikingly little of what astronomers call metals, which is any element heavier than helium. This low metallicity marks them as genuine fossils from the universe's youth. While stars in giant galaxies like our Milky Way are chemical cocktails rich with iron, carbon, and oxygen, the stars in dwarf galaxies are a far more pristine recipe. They are the surviving remnants of a time before countless generations of stars had a chance to seed the cosmos with heavier elements. Studying them is like reading a historical document that has not been edited for billions of years, giving us a direct window into the conditions of the early cosmos. Yet within this chemical simplicity lies stunning complexity. Some of these ancient stars display elemental ratios so bizarre they defy our understanding of how stars create matter. One of the most famous examples involves the element rhenium compared to osmium. In certain dwarf galaxy stars, the amount of rhenium is vastly higher than any known model of stellar nucleosynthesis can explain. It is as if a fundamental recipe of the universe was broken. These stars should not exist according to our textbooks. They suggest there were unique and violent processes in the early universe, ways of forging elements that we have not yet discovered or have long since forgotten. Each of these chemically peculiar stars is a messenger from a bygone era, carrying a fingerprint of events that shaped the cosmos when it was still in its infancy. They force us to rewrite the story of how the elements, the very building blocks of planets and life, came to be. These pristine stellar fossils are the scattered remnants of a much grander construction project. The very existence of our Milky Way, that grand spiral in the night sky, owes its birth to the relentless consumption of countless dwarf galaxies. This is the core of hierarchical structure formation, the universe's great architectural principle. It tells us that the cosmos builds from the bottom up. Small structures form first, and over billions of years they collide and merge, assembling themselves into the colossal galaxies we see today. Your home galaxy was not born a giant. It was painstakingly assembled piece by piece from these smaller cosmic bricks. The evidence for this ancient history is written in the faint outer halo of our galaxy, far from the bright central disk. There, astronomers have mapped vast rivers of stars flowing in great streams across the sky. These are the tidal streams, the final remains of dwarf galaxies that were torn apart by our galaxy's immense gravity. They are the galactic equivalent of archaeological dig sites, preserving the structure of their progenitor galaxies long after they were consumed. One of the most famous of these is the Sagittarius Stream, a great arc of stars that wraps around the entire Milky Way, the final sigh of a dwarf galaxy currently being digested. The stars within these streams carry a distinct chemical passport. They possess a low metallicity, that same primordial signature found in surviving dwarf galaxies, confirming their external origin. They are immigrants, not native-born stars, and their unique chemical makeup allows us to trace them back to their original homes. It is as if we are finding pieces of different ancient pottery scattered around a modern city, each shard telling a story of a different culture that was absorbed long ago. We can even run the clock backwards with sophisticated computer simulations. These models show a frantic, chaotic early universe with hundreds of small, glowing dwarf galaxies swarming in the darkness. Over time, they dance a gravitational dance, slowly spiraling inward, colliding and merging. With each colossal merger, a larger galaxy begins to take shape, its spiral arms settling into place only after the most violent construction phases were complete. This means that the dwarf galaxies we see today are the lucky survivors, the few pieces of the cosmic Lego set that never got snapped into the final structure. They are the living ancestors of giants like the Milky Way, offering us a direct glimpse into the turbulent, creative process that built the universe as we know it. These quiet stellar fossils sometimes explode into chaotic life. A dwarf galaxy can transform into a cosmic fireworks show, erupting in a star-forming frenzy that defies its small size. These are the starburst dwarfs, tiny galaxies that burn with the ferocious energy of a much larger cosmic beast. They create new stars at a rate hundreds or even thousands of times faster than our own Milky Way, a tempest of stellar birth packed into a minuscule volume. What could possibly trigger such a violent and beautiful outburst in a small, fragile galaxy? The most common cause is a close encounter. When two small galaxies brush past each other, or when a dwarf galaxy plows through a dense cloud of intergalactic gas, the resulting gravitational shockwaves can compress vast reservoirs of cold gas. These giant gas clouds collapse under their own weight, igniting countless stellar nurseries all at once. The entire galaxy lights up like a string of firecrackers, blazing with the intense blue light of massive newborn stars. This frantic pace, however, comes at a great cost. A galaxy only has so much gas, the raw fuel for building stars. In a giant spiral, star formation is a slow, regulated process that can last for billions of years. But in a starburst dwarf, the galaxy is essentially burning its entire lifetime supply of fuel in one glorious, extravagant binge. It can consume its entire gas reservoir in a mere 100 million years, a blink of an eye on cosmic timescales. The galaxy is quite literally living fast and dying young, spending its future in a single, brilliant burst of creation. One of the most captivating examples is a galaxy known as Zwicky 18. From afar, it looks less like a galaxy and more like a swarm of glittering diamonds against the blackness of space. Hubble's Space Telescope images reveal a chaotic cauldron of star birth, with brilliant young star clusters and vast, glowing pink clouds of hydrogen gas. The most astonishing thing about Zwicky 18 is its timing. While most galaxies around it formed their stars eons ago, this dwarf is experiencing its very first major burst of star formation, a late bloomer in a universe of aging galaxies. Its stellar population is remarkably young, with many stars just a few million years old. It is a living relic from the universe's early days, a place where the clock of cosmic evolution seems to have been paused, only to start ticking with furious intensity now. These stellar firework displays are not just beautiful, they are a crucial part of the galactic life cycle, a dramatic and fleeting phase that can reshape a small galaxy forever, leaving behind a dense cluster of stars or a quiet, gas-poor relic. This frantic starburst activity can sometimes create entirely new galaxies from the wreckage of the old. Deep within the chaotic tails of gas and dust flung out during a galactic collision, a strange new class of object is born. These are tidal dwarf galaxies, and they defy one of our most fundamental cosmic rules. They are not built from the ground up by dark matter, but are instead assembled from the recycled debris of a cosmic car crash. When two large spiral galaxies tear into each other, their immense gravitational forces act like tidal waves, pulling out vast streams of gas and stars. At certain points along these cosmic rivers, the material can become dense enough to collapse under its own gravity, igniting star formation and forming a new, independent galaxy right before our eyes. We can see this process unfolding in famous collisions like the Antennae galaxies, where bright blue knots of newborn stars dot the long tidal tails, each a potential new dwarf galaxy in the making. What makes these objects so revolutionary is their composition. They are built purely from the baryonic matter, the ordinary atoms that were stripped from their parent galaxies. This leads to a startling conclusion. Tidal dwarf galaxies appear to contain little to no dark matter. They are held together solely by the gravity of the stars and gas we can see. This stands in direct opposition to everything we have learned about classic dwarf galaxies, which are overwhelmingly dominated by dark matter. It suggests the universe has two completely different recipes for building a small galaxy, one anchored by invisible ghosts and the other a purely visible structure. This revelation sparks a fierce debate. Can a galaxy without a dark matter skeleton truly survive? A traditional dwarf is cradled and protected by its massive dark matter halo, which gives it gravitational stability over billions of years. A tidal dwarf born from chaos is a fragile thing. Without that deep gravitational well, could it simply drift apart over time or be easily torn apart by another galactic encounter? Finding a long-lived tidal dwarf galaxy would force us to reconsider the absolute necessity of dark matter in galactic formation. It proves that under the right, albeit violent, conditions, the visible universe can gather itself into an island of stars, creating a cosmic phoenix from the ashes of a collision. Far from the crowded galactic cities, some dwarf galaxies exist in profound solitude. Drifting in the immense, empty voids of the cosmic web, these orphan dwarfs are the loneliest objects in the universe. While most galaxies are drawn into clusters and filaments, these isolated systems inhabit the deserts, the vast billion-light-year expanses of near-nothingness. Their evolution has been one of quiet contemplation, untouched by the violent gravitational tides and searing gas that shape their cousins in the clusters. Without the constant push and pull of neighbors, their star formation is not a frantic burst but a slow, steady burn, a gentle simmer that can last for billions of years. They are cosmic time capsules, preserving a record of a more peaceful and undisturbed path of galactic life. This serene existence presents a direct challenge to our understanding of how galaxies are born. Many of our most successful models suggested that the dense environments of clusters were essential for triggering the collapse of gas and the ignition of the first stars. The immense gravity of a cluster was thought to provide the necessary squeeze to kickstart galactic birth. Yet here are fully formed galaxies thriving in the emptiest regions of space. Their very existence forces us to reconsider the recipe for a galaxy. It seems that even in the deepest voids, where the density of matter is a fraction of what it is elsewhere, nature finds a way to gather gas and light a few stars. A map of the cosmic web tells this story visually. The glowing knots and brilliant filaments of the web are where most galaxies congregate, but if you look closely at the dark, empty patches between them, you will find the faint, solitary pinpricks of light from these orphan dwarfs. They are not failed galaxies, they are a different kind of success, proving that the universe can build islands of stars in the most desolate of oceans. Their quiet, independent lives raise a profound question. If a galaxy can form in total isolation, what does that say about the fundamental forces that sculpt our cosmos? The serene solitude of orphan dwarfs stands in stark contrast to a bizarre and crowded mystery much closer to home. Our own Milky Way is surrounded by a family of small satellite galaxies, and their arrangement is anything but random. These satellites are not scattered around us like a sphere of scattered marbles. Instead, they are organized into a vast, thin, and incredibly flat disk, a great plane of galaxies that rotates in a synchronized dance. This structure, known as the plane of satellites, is a discovery that has left astronomers completely baffled. According to our most fundamental models of cosmic evolution, this should not be happening. The standard cosmological model predicts that dwarf galaxies should be swarming around a giant galaxy in a roughly spherical, random distribution, like bees buzzing chaotically around a hive. What we observe is more like a meticulously arranged carousel, with most of the dwarfs moving along the same narrow track. This precise alignment defies the odds. It would be as if you tossed a handful of coins into the air and they all landed perfectly stacked on top of one another. The probability of this happening by chance is astronomically low, suggesting that our understanding of how galaxies form and gather their satellites is deeply flawed. So what could possibly explain this cosmic synchrony? One compelling theory suggests that these dwarf galaxies did not arrive at our doorstep individually. Perhaps they were all part of a larger group, a single galaxy cluster that was captured by the Milky Way's gravity long ago. As this group was pulled in, its members would have retained their shared motion, naturally explaining why they now orbit in the same plane. It is like a flock of birds being swept up by a large wind current, all moving together in a coordinated fashion. Another, more radical idea points to the shape of the dark matter halo itself. What if the invisible cocoon of dark matter surrounding our galaxy is not a perfect sphere, but is instead significantly flattened like a giant cosmic disk? This elongated shape could naturally shepherd incoming dwarf galaxies into a preferred orbital plane, guiding their paths like marbles rolling around the rim of a bowl. Yet, this explanation also faces serious challenges, as our best simulations of dark matter behavior consistently produce halos that are almost perfectly round. The plane of satellites is not unique to the Milky Way. Our nearest large neighbor, the Andromeda Galaxy, also has its own set of dwarf galaxies arranged in a similar, vast rotating plane. This fact deepens the mystery exponentially. It means that whatever process is creating these structures, it is not a rare fluke. It is a fundamental feature of how giant galaxies are built, a pattern we have been missing all along. This great celestial carousel forces us to question the very scaffolding of the cosmos. This great celestial carousel is not the only thing shattering our expectations of small galaxies. Deep within the tranquil hearts of some dwarf galaxies, astronomers have uncovered monsters. They have found supermassive black holes, gravitational behemoths that were supposed to be the exclusive property of giant galaxies like our own. This discovery upends a fundamental rule of cosmic architecture. We always thought that a supermassive black hole, an object weighing millions or even billions of times the mass of our Sun, could only grow in a massive galaxy. The logic was simple. A large galaxy provides a vast buffet of gas and stars to feed the central beast, allowing it to grow to such immense proportions. But now we know that is not the whole story. Inside small, quiet dwarf galaxies, black holes of shocking size are lurking. How did they get there, and what does their existence tell us about the infancy of the cosmos? The leading theory is as profound as it is simple. These black holes are not overgrown newcomers. They are ancient relics, the original seeds from the dawn of time. In the chaotic aftermath of the Big Bang, the very first stars to ever form were colossal, short-lived behemoths. When they died, they collapsed, potentially creating black holes of a few hundred solar masses. These were the primordial seeds. In most giant galaxies, these seeds feasted for billions of years, merging and gorging on gas to become the supermassive black holes we see today. But in these dwarf galaxies, the seeds never got their meal. The galaxy simply did not have enough gas to feed them, so they have sat there, mostly dormant, for over 13 billion years. They are the sleeping giants of the cosmic deep, fossils from an era before galaxies even finished forming. Finding them is a tremendous challenge. Since they are not actively feeding, they do not blaze with the intense radiation of a quasar. Astronomers have to use clever, indirect methods to hunt them down. They look for the subtle but telltale motions of stars whipping around the galaxy's core at incredible speeds. This frantic stellar dance can only be caused by the immense gravitational pull of an incredibly massive, compact object, a hidden black hole. One of the most compelling examples is a dwarf galaxy named Reticulum 2. It is one of the Milky Way's own tiny satellites, a faint smudge of stars. Yet, measurements of the motions of its stars revealed a startling gravitational signature at its center, pointing to a black hole with a mass of more than 100,000 suns. This is a behemoth residing in a cosmic village. The implications are staggering. If these dormant giants are common in dwarf galaxies, then they are the missing links in the story of how supermassive black holes came to be. Every giant black hole, like the one at the heart of our Milky Way, must have started as one of these small seeds. By studying the black holes in dwarfs, we are looking at the humble beginnings of the most powerful engines in the universe. They are the infants that never grew up, offering us a pristine view of a chapter in cosmic history we thought was lost to time. These sleeping giants in dwarf galaxies hint at a cosmic architecture far stranger than we first imagined. Another profound mystery lurks in the shadows of our own galactic backyard, a puzzle so sophisticated it is called the too big to fail problem. The name itself is a cosmic irony. Our most advanced supercomputer simulations of the universe create a very specific prediction for the Milky Way's neighborhood. They tell us that the most massive dark matter halos orbiting our galaxy should be absolute powerhouses. These halos have such deep gravitational wells, such immense pulling power, that they should have easily held onto vast amounts of gas in the early universe. That gas should have collapsed to form stars, creating the brightest, most massive, and most star-rich dwarf galaxies in our cosmic vicinity. According to the simulations, these dwarfs should be teeming with stars, shining brilliantly and impossible to miss. They are, in theory, too big and too gravitationally powerful to have failed at the fundamental task of galaxy formation. But when we look at the actual dwarfs orbiting the Milky Way, the story is completely different. The galaxies living in these predicted powerhouse halos are not mighty. They are incredibly faint, some of the most ghostly and star-poor objects we have ever found. It is as if we predicted a bustling, neon-lit metropolis and found instead a tiny, quiet village with only a few streetlights. The dark matter halos seem to be there, as predicted, but they are filled with a paltry number of stars, far fewer than their immense gravitational strength should have allowed them to gather. This creates a serious tension between our theoretical models and observed reality. If the standard model of cold dark matter is correct, then why are these cosmic titans so dim? One compelling explanation involves the devastating effects of the early universe. Imagine a young, small dwarf galaxy just beginning to form its first stars. These first stars are often massive and hot, and they flood their surroundings with intense ultraviolet radiation. In a small galaxy with a weak gravitational hold, this radiation can be powerful enough to blow away the remaining gas, the very fuel for future stars. The galaxy effectively sterilizes itself, shutting down star formation before it can ever truly take off. The dark matter halo is indeed massive and powerful, but its visible galaxy was strangled in its cradle. Another fascinating possibility strikes even closer to the heart of our models. Perhaps the dark matter halos themselves are not as dense as our simulations assume. The standard cold dark matter model predicts that halos should have incredibly dense, cuspy centers. But if dark matter has even a tiny ability to interact with itself, to collide and scatter, it could smooth out these dense central cusps. This would create a halo with a softer, less concentrated core. With a gentler gravitational center, the halo would be less effective at pulling in and holding onto the gas needed to form a brilliant galaxy. The halos would still be massive, but their power would be distributed, not focused, making them far less efficient at building stellar cities. This too big to fail problem forces us to look at every faint dwarf galaxy in a new light. They are not just failed galaxies, they are cosmic experiments testing the very nature of the invisible dark matter that makes up most of our universe. Each faint smudge of starlight is a question mark, challenging us to determine if we need to rewrite the rules of dark matter itself. The too big to fail problem shakes the very foundation of dark matter theory, but another discovery threatens to tear the whole structure down. Astronomers have found galaxies that appear to contain no dark matter at all. This should be impossible. The first of these cosmic rule breakers is a ghostly giant known as NGC 1052 DF2. From the outside, it looks like a typical ultra-diffuse galaxy, a large, faint smudge of light. but when scientists measured the motions of its star clusters, they found something that defied all logic. The clusters were moving slowly, far too slowly for a galaxy of its size if dark matter were present. The calculated total mass of the galaxy based on these motions matched almost perfectly with the mass of its visible stars and gas. There was simply no room left for dark matter. It was a galaxy made of purely ordinary matter, a cosmic heresy. The discovery was met with immediate and intense skepticism. The central debate hinged on a single, crucial number, the galaxy's distance. If DF2 was much closer to us than initially thought, its mass calculations would be wrong and dark matter could slip back into the picture. One team of researchers argued fiercely for this closer distance, using a different set of observational methods. The original discovery team held their ground, presenting further evidence that confirmed their initial distance measurement. The scientific community watched a high-stakes debate unfold, with the credibility of a monumental finding hanging in the balance. Then, a second galaxy was found, NGC 1052 DF4, showing the same bizarre lack of dark matter. Finding one might be a fluke, but finding two suggests a pattern. The existence of these galaxies creates a paradox just as profound as those dominated by dark matter. If our models are correct, dark matter is the essential scaffolding for all galaxies. How could a large, stable galaxy form without this invisible skeleton holding it together? Its stars should have simply flown apart. The presence of dark matter-free galaxies forces us to consider that galaxy formation is far more diverse and complex than we ever imagined. It proves that the universe has more than one way to build an island of stars. The debate is far from over, with new observations and analyses published every year. This is not just an academic argument, it is a battle over the fundamental rules of the cosmos, and the final verdict is still out. This profound paradox of galaxies with no dark matter leads us to a completely different kind of cosmic fossil, one frozen in time. Some dwarf galaxies are not defined by what they lack, but by what they have refused to become. These are the relic galaxies, celestial time capsules that have remained virtually unchanged for over 10 billion years. While the rest of the universe swirled into grand spirals and colossal ellipticals, these ancient islands simply stopped. Their star formation ceased in the distant past, and they have drifted through the eons in perfect isolation, never merging, never colliding, never reigniting. They are the universe's greatest recluses, preserving a snapshot of a much younger cosmos. The stars within them are exclusively old population 2 stars, blazing with a cool, red light and composed almost entirely of hydrogen and helium. There are no young, blue stars here, no glowing pink nebulae giving birth to new suns. The galaxy's gas was either used up in one initial, frantic burst of creation or blown away by those first massive stars, and it was never replenished. The result is a stellar population that is uniform, ancient, and incredibly pristine. Studying one of these relics is the closest we can get to time travel. It allows us to examine the properties of the very first generations of stars, objects that are long gone in every other galaxy. How massive were these first stars? How quickly did they form? The answers are locked in the faint, red glow of these frozen systems. One of the most promising candidates for a relic galaxy is a faint dwarf in the constellation of Cetus, known as Tucana II. Observations reveal it is incredibly metal-poor, even for a dwarf galaxy, suggesting its star formation was both early and brief. Its stars are all remarkably similar in age and composition, a hallmark of a system that had a single, defining period of activity before falling silent. The challenge, of course, is confirmation. How can we be sure a galaxy is a true relic and not just a quiet, aging system that formed its stars slowly over time? Astronomers must perform a kind of galactic archaeology, using the color and brightness of every single star to reconstruct its history. They look for the complete absence of any youthful blue stars and measure the precise chemical signatures in the ancient red ones. Finding a confirmed relic galaxy is like discovering a lost city untouched by modern civilization, a place where we can walk among the original structures and understand the world as it was at the very beginning. These silent red islands hold the original blueprints of galactic construction, offering us an unedited look at the universe's first chapters. The silent red islands of relic galaxies are anchored by a hidden architecture far grander than we ever suspected. We now discover that the dark matter enveloping dwarf galaxies is not a small, tight cloak. It is a colossal, tenuous sphere that stretches for hundreds of thousands of light years, a vast invisible ocean in which the galaxy's visible stars are merely a tiny, glittering raft. The stars we see mark only the very heart of a much larger, more massive entity. How can we possibly map something we cannot see? Astronomers use the galaxy's own far-flung citizens as tracers. By pinpointing individual ancient stars that were gravitationally ripped away in past encounters, they can trace the galaxy's true gravitational reach. These distant stars orbit in the extreme outer darkness, moving according to the pull of the unseen halo. Another method watches the behavior of clouds of cold hydrogen gas that surround the dwarf. This gas is not bound tightly to the stars, but it is trapped within the immense gravitational grip of the dark matter halo. By measuring the rotation of this gas, scientists can weigh the entire invisible structure, revealing its staggering total mass and its expansive shape. The resulting picture is humbling. A dwarf galaxy that appears as a small smudge of light in a telescope is actually the central highlight of a dark matter sphere that could easily engulf the entire Milky Way. This immense size relative to the small visible galaxy creates an incredibly low density. The dark matter is so thinly spread that its gravitational influence is subtle, a gentle, pervasive pull across an incomprehensible volume. This very distribution holds the key to unlocking dark matter's identity. The way dark matter particles are thought to clump and spread depends entirely on their fundamental properties. Are they cold, moving slowly and clumping into dense centers? Or are they warm, moving faster and resisting that dense packing, resulting in the more spread-out halos we observe? The extended nature of these halos strongly suggests that dark matter particles must have a certain minimal velocity, an inherent warmth that prevents them from collapsing into the ultra-dense cusps predicted by the simplest models. This single observation from the faintest galaxies in the sky rules out entire classes of theoretical particles. It tells particle physicists on Earth which of their complex equations might be worth pursuing and which are cosmic dead ends. The grand, invisible architecture of a dwarf galaxy is not just a curiosity. It is a direct message from the dark sector itself, written in the language of gravity and waiting to be decoded. This silent death of a galaxy is a cosmic event known as quenching. A quenched dwarf is a galaxy that has been sentenced to a kind of eternal stillness, its fires of creation extinguished forever. While massive galaxies can experience multiple bursts of star formation, a small dwarf galaxy often gets just one chance. When its gas is gone, the party is over for good. The question is, what cosmic force delivers this final sentence? Astronomers have identified several chillingly effective kill mechanisms. One of the most dramatic is ram pressure stripping. Picture a small, isolated dwarf galaxy, happily holding onto its reservoir of cold gas, the raw material for building new stars. Now, imagine this dwarf falling for the first time into the dense, crowded environment of a giant galaxy cluster. As it plummets through this region, it encounters a hot, thin, but pervasive soup of intergalactic gas. For the dwarf moving at incredible speeds, this gas feels like a hurricane-force wind. The pressure is so intense that it acts like a cosmic broom, violently sweeping the galaxy's own gas right out of its gravitational grasp. The stars, held tight by gravity, remain untouched. But the precious fuel for future generations is blown away into the void, leaving the galaxy gasping and barren. It is a galactic mugging, a swift and violent death. Another, more insidious fate is strangulation. This is a slower, more drawn-out end. If a dwarf galaxy becomes a satellite of a much larger galaxy, like our Milky Way, it can be cut off from its supply of fresh cosmic fuel. The large galaxy's gravitational pull and its vast halo of hot gas can prevent new, pristine hydrogen from the cosmic web from ever reaching the small dwarf. The dwarf is left to burn through only the gas it already has inside it. It continues forming stars until that last tank of fuel is exhausted. Once it's gone, there is no replenishment. The galaxy slowly suffocates, its star formation rate sputtering out as it slowly bleeds to death. Why does this cosmic death sentence matter so much? Understanding quenching is not just about explaining why some dwarfs are red and dead while others are blue and vibrant. It is about decoding the universal life cycle of all galaxies, including our own. These small galaxies are the test cases, the simple organisms that reveal the fundamental rules of galactic evolution. In a giant galaxy, the processes of star formation and quenching are complex and overlapping, a messy history that is incredibly difficult to untangle. But in a dwarf, the story is often stark and simple. It is a single, clear event written in the ages of its stars. By studying the corpses of these quenched dwarfs, we can read the autopsy report and determine the exact cause of death. Was it a violent encounter or a slow, resource-deprived fade? The answer tells us how the environment of the cosmos shapes the destiny of everything within it, from the smallest island of stars to the grandest spiral. These faint ghosts of the cosmos can sometimes act as cosmic magnifying glasses. It seems impossible. A dwarf galaxy with so few stars should not possess enough gravity to noticeably bend the fabric of space around it. Yet, against all odds, we have observed the telltale signs of this very phenomenon. When a dwarf galaxy aligns almost perfectly with a far more distant, brilliant object like a quasar, its immense, concentrated dark matter halo warps the space in between. This transforms the dwarf into a gravitational lens, bending and focusing the light from the background source. The result is a celestial mirage, a distorted image of the distant quasar stretched into a perfect, shimmering circle of light known as an Einstein ring. These rings are incredibly rare and delicate, a signature of gravity's invisible hand at work. Hubble's Space Telescope images have captured these ethereal structures, where a faint, foreground dwarf galaxy is encircled by a thin, blue ring of distorted starlight that does not belong to it. This is the light from a galaxy billions of light years further away, its path twisted into a perfect halo by the dwarf's unseen mass. This lensing effect is the universe's own scale. It allows astronomers to directly weigh the dwarf galaxy's total mass, including its dominant dark matter component, in a way that is completely independent from measuring starlight or stellar motions. The size and shape of the Einstein ring are a direct function of the lensing galaxy's gravitational strength. By analyzing the ring, scientists can calculate the total mass of the dwarf with stunning precision. Every time, the result is the same, a confirmation of the dark matter dominance we first suspected from stellar motions. The visible stars account for a mere fraction of the gravity required to create such a profound distortion of space. These cosmic mirages provide the most direct and undeniable evidence that these small galaxies are anchored by colossal, invisible anchors. They are not just inferring dark matter's presence, they are mapping its distribution by seeing how it bends light from the background universe. This turns a faint smudge of stars into a precise scientific instrument, a natural telescope that reveals the hidden architecture of the cosmos itself. These faint cosmic mirages hide a force far more tangible than gravity. A recent discovery has revealed that some dwarf galaxies generate magnetic fields of shocking strength and complexity. These invisible fields weave through the interstellar void, shaping the paths of cosmic rays and the collapse of gas clouds. We have long believed that such powerful, organized magnetism was the exclusive product of a dynamo effect, a process that requires a large, rapidly rotating galaxy. Like a spinning turbine generating electricity, the churning motion of a giant spiral's disk was thought to be essential for amplifying a seed magnetic field into a galaxy-spanning force. Finding these robust fields within small, often irregular, and slowly turning dwarfs shatters that assumption entirely. It suggests that the seeds of magnetism were planted in the universe much earlier than anyone predicted, perhaps even before the first galaxies fully formed. One of the most compelling examples is a dwarf galaxy known as IC10. Observations from radio telescopes show a stunning map of polarized light, a visual representation of the magnetic field lines tracing the galaxy's structure. The lines are not chaotic and weak as one might expect from a small, turbulent system. They are coherent and surprisingly well-ordered, stretching across vast distances within the dwarf. This presents a fundamental puzzle. Without the powerful engine of a large galactic dynamo, what is generating and sustaining these fields? The answer may lie in the very beginnings of star formation itself. The first massive stars to ignite in a dwarf galaxy live fast and die young, exploding as supernova. These colossal detonations do not just release chemical elements, they also blast out shockwaves that can compress and twist any weak, primordial magnetic fields, potentially strengthening them dramatically. Furthermore, the frantic star-forming activity common in many dwarfs could be creating a small-scale, but intensely powerful, dynamo of its own, driven by stellar winds and supernova bubbles rather than the rotation of an entire galactic disk. The implications ripple outward, touching the very process of creation. Magnetic fields play a crucial role in star formation. They provide support against the gravitational collapse of giant gas clouds, regulating how quickly and efficiently new stars are born. A stronger magnetic field can slow down star formation, effectively putting the brakes on a galaxy's development. The presence of these unexpectedly powerful fields in dwarf galaxies could be a key reason why some of them form stars so slowly, or why they stop forming stars altogether. It is a hidden hand, an invisible framework that guides the evolution of these small islands. This discovery forces us to rewrite the story of cosmic magnetism. It was not a luxury that only large, mature galaxies could afford. It was a fundamental part of the recipe from the very start, a silent, powerful player in the construction of the cosmos, woven into the fabric of even its smallest structures. These unexpectedly powerful magnetic fields shape the very raw material of creation, and sometimes that material is a perfect relic. Deep within the silent voids and quiet corners of dwarf galaxies, astronomers have found reservoirs of cold hydrogen gas that are almost perfectly pristine. This gas is a direct fossil, a surviving pocket of the original matter from which the first galaxies coalesced. It has remained virtually untouched by the complex chemistry of stellar life and death. While the gas in a galaxy like our Milky Way is a polluted soup, enriched with carbon, oxygen, iron, and silicon from countless supernovae, this primordial gas is a simple broth of just hydrogen and helium. It is the universe in its purest, most elemental form. Finding it is like discovering a hidden spring that has been sealed off from the world since the dawn of time, its waters completely unchanged. The survival of this pristine gas is a minor miracle. In a large galaxy, the continuous cycle of star formation and destruction constantly churns and enriches the interstellar medium. But in these isolated, quiescent dwarf galaxies, star formation was either incredibly feeble or happened in a single, brief burst that did not produce enough heavy elements to contaminate the entire system. The galaxy essentially used up its small supply of dense gas to make a first generation of stars, and the vast majority of its remaining hydrogen was left floating in a diffuse halo, never cycled through a stellar furnace. This gas has been sleeping for billions of years, a sleeping giant of potential that was never awakened. The importance of this discovery cannot be overstated. This pristine gas gives us the initial conditions. It is the blank canvas upon which the first galaxies were painted. By studying its density, temperature, and distribution, we can understand the exact properties of the raw fuel that was available for the very first stars. How easily did it collapse? What was the typical size of the first star-forming clouds? These clouds are the control group in the cosmic experiment, showing us what the universe was like before stars changed everything. They hold the key to understanding why some small galaxies lit up with brilliant starbursts while others remained dark and dormant. These silent, chemically simple reservoirs are more than just fossils. They are a preserved recipe from the universe's first kitchen, waiting to tell us how everything began. The silent, pristine gas clouds of dwarf galaxies are the raw fuel of creation, but they also reveal a far more violent side of cosmic evolution. The Milky Way is not a gentle giant. It is a predator, and the evidence of its ancient feasts is written across the sky in faint, flowing rivers of stars. These are tidal streams, the final, dissolving remains of dwarf galaxies that were torn apart and consumed by our galaxy's immense gravity. They are the ghostly scars of galactic cannibalism, and they tell the story of how our home was built. The most famous of these is the Sagittarius Stream, a great arc of stars that wraps around the entire Milky Way like a faint celestial ribbon. It is the final sigh of the Sagittarius dwarf elliptical galaxy, a small system that is currently in the process of being digested. Its stars are being pulled away, stretched into long trails that trace the precise path of their orbital decay. This is not a static monument, it is a crime scene in slow motion, and astronomers are the detectives. By measuring the positions, motions, and chemical compositions of the stars within these streams, they can perform a kind of galactic forensic reconstruction. They can rewind the clock, tracing the stream backwards to determine the exact size, mass, and orbit of the original dwarf galaxy before it was devoured. It is like finding a fossilized bone and using it to reconstruct the entire skeleton of a long-extinct creature. But these streams do more than just recount past mergers. They are the most precise tools we have for mapping the invisible architecture of our own galaxy. The path a tidal stream takes as it orbits the Milky Way is exquisitely sensitive to the shape and distribution of our galaxy's dark matter halo. The dark matter's gravity is the puppet master, and the stream of stars is the puppet, its dance revealing the master's every move. If the dark matter halo were a perfect sphere, the streams would follow certain predictable paths. But observations show they are often twisted and contorted, their shapes telling us that the Milky Way's dark matter halo is not a sphere at all, but a triaxial ellipsoid, a shape more like a colossal cosmic potato. An all-sky map of these stellar streams would show a stunning complexity. Dozens of faint, luminous ribbons encircling our galactic center, each one the ghost of a separate meal, each one a data point in the most detailed map of our invisible gravitational landscape we will ever have. These streams are more than just remnants of destruction. They are the threads that weave together the history of our galaxy, revealing a past built on a foundation of relentless consumption and growth. The serene image of a dwarf galaxy as a simple, ancient relic is another assumption crumbling to dust. We once thought these small systems were monolithic, containing only a single, uniform population of old stars. But the stellar census tells a far more complex story. Some dwarf galaxies, especially the spherical dwarf ellipticals that orbit giants like Andromeda, are cosmic palimpsests. They contain multiple, distinct generations of stars, each with its own age and chemical signature, layered on top of one another. A single, faint smudge of light in a telescope resolves into a tapestry of cosmic history. The oldest stars are there, blazing with a cool, red light and bearing the pristine fingerprint of only hydrogen and helium. Yet mixed among them are brighter, younger stars, their blue-white color and slightly richer chemical makeup betraying a later birth. This is a galaxy that lived more than one life. How does a small galaxy with its limited resources manage to reignite its engines of creation? The answer points to a surprisingly eventful past. A quiet, isolated dwarf might only have one chance to form stars, using up its initial gas supply. But a dwarf that experiences a merger with an even smaller companion, or that slowly accretes a fresh stream of intergalactic gas over billions of years, can receive a second wind. This new infusion of fuel collapses under gravity, triggering a new, delayed epoch of star formation. The galaxy writes a new chapter over its ancient text. Astronomers unravel this history by creating intricate color-coded star maps. Imagine a map of a dwarf galaxy where every dot of light is not just a star but a data point. The oldest, reddest stars are painted in deep crimson. The intermediate age stars appear in yellow and orange. The youngest, most energetic populations shine in brilliant azure. The resulting image is not a uniform blob of red. It is a layered portrait, often revealing that the younger, bluer stars are concentrated in the galaxy's core, while the ancient red stars form a more extended, diffuse halo. This structure tells a clear story. The first generation of stars formed throughout the entire primordial cloud of gas. Then, billions of years later, a fresh supply of gas drifted inward, settling in the dense central regions and lighting up with a final, brilliant burst of new stellar life. This complexity forces us to abandon the idea of dwarf galaxies as simple, one-note fossils. They are dynamic entities with their own unique biographies, shaped by quiet accretion and violent mergers just like their giant cousins. Unlocking the sequence of events within a single dwarf galaxy gives us the master key to understanding the full spectrum of galactic evolution, from the smallest island to the grandest spiral. The universe refuses to be simple, even in its most humble corners. This vibrant blue light signals a cosmic rebirth. Blue compact dwarf galaxies are the universe's most intense stellar nurseries, tiny islands ablaze with the fierce light of newborn suns. Their intense blue color comes not from a mix of stars, but from a single, dominant population, massive, hot, young stars that burn brilliantly and die young. These galaxies are not just forming a few new stars, they are undergoing a galaxy-wide firestorm of creation. A starburst so extreme it can transform the entire system in a cosmic instant. They are often incredibly metal-poor, their gas lacking the heavy elements forged in previous generations of stars. This pristine chemical state suggests we are witnessing a galaxy's first great awakening, its very first major burst of star formation after billions of years of quiet slumber. It is like finding a civilization that has just discovered fire for the first time. What triggers such a dramatic and delayed ignition? The catalysts are often violent and beautiful. A close gravitational encounter with a neighboring galaxy can send shockwaves rippling through a dwarf's gas reservoirs, compressing vast clouds and sparking a chain reaction of collapse. Alternatively, the slow, steady accumulation of intergalactic gas over eons can finally reach a critical density, a tipping point where the entire system gives way to a frenzy of stellar birth. One of the most stunning examples is a galaxy known as Hennies 210. From a distance, it looks like a shattered sapphire, a chaotic collection of brilliant blue star clusters tangled within glowing pink nebulae. The entire core is a factory for massive stars, with some clusters so young they are still embedded in their natal cocoons of dust. The importance of these blue dwarfs reaches back to the dawn of time. They are our local windows into the early universe. The first galaxies to ever form were also metal-poor, composed of nothing but pristine hydrogen and helium. By studying a blue compact dwarf like Hennies 210, we are witnessing the same physical processes that lit up the cosmic dark ages, the same furious birth of stars in a simpler, more elemental cosmos. They show us how the very first stellar factories operated, free from the complex chemistry that governs star formation in older galaxies like our own. These brilliant blue beacons are more than just a pretty sight. They are active experiments in the fundamental physics of creation, showing us how stars are born when the universe itself was still in its raw, primordial youth. This brilliant blue light from the earliest dwarf galaxies did more than just decorate the cosmos, it fundamentally transformed it. These tiny, energetic systems are now the prime suspects in one of the universe's most dramatic events, the epoch of reionization. For hundreds of millions of years after the Big Bang, the universe was a featureless, soupy fog. Space was filled with a thick cloak of neutral hydrogen gas that scattered light, rendering the entire cosmos opaque. It was a dark age, a time when no free-flying light could travel across the void. Then something happened. Something began to tear that fog apart, atom by atom, until the entire universe became the transparent, crystal-clear expanse we see today. The leading theory points directly to the collective power of countless dwarf galaxies. While a single giant galaxy might be rare and slow to form, the universe was teeming with these small, agile stellar factories. Each one, blazing with massive, hot, young stars, acted like a tiny lighthouse in the primordial murk. These stars did not just emit visible light, they flooded their surroundings with a torrent of high-energy ultraviolet radiation. This UV radiation is incredibly powerful, enough to smash into a neutral hydrogen atom and rip its electron clean away, a process known as ionization. One dwarf galaxy could create a small, transparent bubble around itself, but multiplied by millions, even billions of these galaxies scattered across the early cosmos, their individual bubbles began to overlap and merge. It was a slow, cosmic dawn, a gradual burning away of the fog until the entire universe was reionized, its hydrogen atoms permanently stripped of their electrons, allowing light to travel freely for the first time. The evidence for this monumental role is mounting. When we look at the most distant quasars, their light tells a story of having passed through increasingly patchy and ionized gas, a timeline that aligns perfectly with the peak era of star formation in the earliest dwarf galaxies. The sheer number of these small systems, calculated from our deepest surveys, suggests they could have produced more than enough UV radiation to get the job done, a collective effort that giant galaxies alone could not have managed. This is precisely why the hunt for the faintest, most primordial dwarf galaxies is a primary mission for the James Webb Space Telescope. Its infrared eyes are designed to peer back to the very edge of this reionization epoch, to directly spot the tiny, faint glows of the galaxies that cleared the cosmic stage. Finding them and confirming their overwhelming numbers would close the case on one of the greatest transformations in cosmic history, revealing how the smallest islands of stars worked in unison to illuminate the entire universe. Yet this grand picture of dark matter's invisible ocean is not the final word. The true mystery lies in its hidden topography, the precise way this mysterious substance is arranged deep within a galaxy's heart. Our most powerful computer simulations, based on the standard model of cold dark matter, give us a very specific prediction. They tell us that a dwarf galaxy's dark matter halo should have a sharply peaked center, a dense, intense cusp where the invisible particles are packed together incredibly tightly. Imagine a mountain with an impossibly steep and narrow peak, where the density soars to incredible heights right at the very center. That is the cusp profile, and for decades it was the accepted blueprint for every dark matter structure in the universe. But when astronomers look at the actual stars inside real dwarf galaxies, they find a story that does not match this prediction at all. By carefully tracking the motions of these stars, they can map out the gravitational field, and therefore the distribution of the unseen mass pulling on them. Over and over, the stellar motions suggest something far different from a sharp peak. They point toward a core, a central region where the dark matter density is much more uniform, like a flattened hill with a gentle, rolling summit instead of a jagged spire. This glaring mismatch between what our simulations predict and what we actually observe is known as the core cusp problem, and it is one of the most significant cracks in the foundation of modern cosmology. If dark matter behaves exactly as the standard model says, then these dense cusps should be everywhere. Their consistent absence is a major red flag. One compelling solution proposes that dark matter is not entirely dark after all. What if dark matter particles can interact with each other? This idea, known as self-interacting dark matter, suggests that these invisible particles can actually collide and scatter, much like billiard balls. In a dense forming galaxy, this self-interaction would act like a form of friction. Particles from the crowded, high-density outer regions of the forming cusp would bump into each other, transferring energy and moving inward. This process would naturally smooth out the sharp central peak, redistributing the dark matter into a much shallower, flatter core. It is a simple and elegant fix, but it requires a fundamental change to the properties of the universe's most dominant substance. The implications of this debate are immense. The presence of a core instead of a cusp could explain other dwarf galaxy mysteries, like why some are so faint. A dense cusp provides a strong, focused gravitational anchor, perfect for pulling in gas and forming stars. A soft, diffuse core offers a much weaker pull, making it far easier for a galaxy to lose its star-forming fuel and become a dark, quenched relic. The core cusp problem is not just a technical argument, it is a direct challenge from the smallest galaxies, forcing us to ask if we have truly understood the nature of the invisible cosmos. Their slow, steady lives could make dwarf galaxies the ultimate cosmic survivors. While giant galaxies like our Milky Way blaze brightly for billions of years, they are locked in a gravitational dance that will inevitably lead to violent collisions and a final, aging fade. The isolated dwarf galaxies drifting in the great voids, however, face a very different future. Untouched by the chaos of galactic cities, they will continue their quiet existence, burning through their remaining hydrogen fuel at a glacial pace. Their star formation, already a faint simmer, could persist for trillions of years, long after the last massive stars in larger galaxies have died. These cosmic small fry may become the last bastions of stellar light in an increasingly dark and aging universe, outliving every giant that once overshadowed them. But this serene fate is not for all. For the satellite dwarfs already caught in a giant's grasp, like our own large and small Magellanic Clouds, the future is one of certain destruction. They are on an inescapable spiral inward, destined to be torn apart by the immense tidal forces of the Milky Way. Their stars will be stripped away, joining the great rivers of tidal streams that already encircle our galaxy. This is not an end, but a transformation. The material from these devoured dwarfs will be recycled, becoming part of the Milky Way's next generation of stars, a final contribution to the galaxy that consumed them. This grand cycle of creation and destruction culminates in the most dramatic event in our local universe's future, the colossal merger between the Milky Way and the Andromeda Galaxy. When these two giants collide in billions of years, their dance will not be a gentle one. The space between them will be filled with a storm of gravitational chaos, and the dwarf galaxies orbiting both will be swept up in the turmoil. Their orderly orbits will be scrambled, with many being flung into intergalactic space while others are drawn into the heart of the new, larger galaxy that forms from the wreckage. This ultimate fate reveals the profound duality of dwarf galaxies. They are both the universe's most enduring relics and its most ephemeral building blocks. Some will witness the end of all stellar creation in serene isolation, while others will be sacrificed to build the galactic giants of tomorrow. Their diverse life cycles, from quiet birth to dramatic dissolution, prove that even the smallest structures hold a mighty role in the eternal story of the cosmos. Our journey through 25 cosmic enigmas reveals a universe transformed. These dwarf galaxies, once dismissed as simple celestial backdrops, have emerged as the central characters in the greatest story ever told. Their faint starlight illuminates the dark matter that binds the cosmos. Their ancient chemistry holds the recipe for the first stars. Their violent births and quiet deaths map the entire life cycle of galactic evolution. We chased the ghosts of ultra-diffuse galaxies and found them anchored by invisible giants. We witnessed starbursts that blaze with the fury of a youthful cosmos and discovered relic galaxies frozen in time. We grappled with the paradox of galaxies missing their dark matter and others that seem to be made of nothing else. From the great plane of satellites to the hidden black holes sleeping in their cores, every discovery proves that size is no measure of significance. These smallest of galaxies hold the keys to the largest of questions. They taught us that our own Milky Way is a cannibal built from the remains of countless dwarfs. They showed us how their collective light burned away the primordial fog, clearing the stage for the universe we see today. They challenged the very nature of dark matter, forcing us to rewrite the rules of physics itself. So the next time you gaze at the night sky, remember this. Beyond the bright band of the Milky Way, in the vast, dark spaces between the stars, countless dwarf galaxies drift in silence. They are the architects and the fossils, the builders and the ghosts. They are the quiet, persistent heartbeat of the cosmos, and their mysteries are still unfolding. What cosmic secret will they reveal next? We would love to hear your thoughts. Which of these strange discoveries surprised you the most? Share your questions and your wonder in the comments below.